For as long as Earth has existed, the moon has been locked beside us, stabilizing our tilt, shaping our oceans, and setting the rhythm of the planet without ever saying a word. It feels permanent, and like something that will always be right where it is at night. But when scientists began bouncing laser pulses off reflectors left on the lunar surface, they discovered something no one expected at the time. The moon is drifting, changing its distance from Earth with every passing year. And that tiny movement adds up to a future where the moon becomes too far away to play the role it does today. When people first started talking about the moon drifting away, it sounded like one of those abstract, long timescale facts you'd only find in a textbook. But then we built something that made it measurable, down to the millimeter. You see, during the Apollo missions, astronauts left behind small panels on the moon covered in reflectors. Today, scientists fire lasers at them from Earth, waiting for the beam to bounce back and time the round trip with absurd precision. And when you do that every day, year after year, a pattern starts to show up. Once that became clear, researchers checked older geological records, tidal patterns, even ancient eclipse timings, and everything lined up. The moon has been drifting outward for hundreds of millions of years. And the rate we measure today is a part of a long, ongoing process. Because the moon is the active part of Earth's machinery. Its gravity pulls on our oceans, creating tides strong enough to move entire coastlines twice a day. It helps keep Earth's rotation in check, acting like a stabilizer that prevents our planet from spinning too fast. And maybe most importantly, the moon anchors the tilt of Earth's axis. Without it, that tilt would wander more dramatically, shifting climates, reshaping seasons, and making the planet far less predictable over long periods of time. Right now, the moon is close enough to keep all of that stable, but as the moon drifts away, every one of those systems begins to change. And the farther it goes, the harder it is for the moon to keep doing the job it's been doing for billions of years. The more you look at what the moon holds together, the easier it is to see why even a slow drift matters. Tides are the first thing to change. Right now, the moon's pull is strong enough to lift entire oceans by meters. Those tides mix nutrients, shape coastlines, and even influence marine life cycles. As the moon inches outward, that pull weakens. Earth's rotation shifts too. The moon kind of acts like a brake, stealing a tiny bit of Earth's rotational energy and drifting outward as a result. That's why the days are getting longer by fractions of seconds each century. And then there's Earth's tilt, the thing that gives us seasons. The moon keeps that tilt steady, preventing wild swings that could turn climate patterns chaotic. As it retreats, its stabilizing grip weakens. Not enough to notice now, but the trend is there. And it raises the next question. How fast is the moon actually leaving us? And when does the change start to matter? The moon drifts away from us by about 3.8 centimeters per year. It doesn't sound like much, but over long timescales it becomes a major shift. Millions of years of that steady outward movement slowly reshape the entire Earth-Moon system. And because the drift is tied to tidal friction, the rate isn't perfectly constant. As Earth's rotation continues to slow, the moon's outward spiral gradually changes with it. When researchers ran the clock backward, using the drift rate we measure today, the picture that formed was nothing like the world we live in now. Early in Earth's history, the moon sat far closer, so close that it dominated the sky. Its pull on our oceans was so strong that it would reshape coastlines and push water around the planet with a force that would feel almost alien today. Earth itself was spinning much faster at the time, giving the planet shorter days and a more restless environment overall. As time passed, Earth lost some of its rotational energy to the tides it created. The oceans became less violent, Earth's spin slowed to something closer to what we recognize, and the climate became more stable over long stretches of time. By the time the moon reached its current distance, the system had calmed enough for the long-term patterns we depend on to lock in. And all of that came from a process so small each year you'd never notice it, but powerful enough over millions of years to reshape an entire planet. As precise as those measurements are, they leave one question at the center of the entire problem. How far can the moon drift before its influence on Earth becomes fundamentally different from what it is today? To answer that, researchers model how the Earth-Moon system evolves as tidal friction continues to slow Earth's rotation. As the planet turns more slowly, the efficiency of that energy transfer drops, and the moon's outward drift gradually decelerates. But even with that slowdown, the cumulative change over hundreds of millions of years is enormous. Eventually, the moon reaches a distance where its gravitational pull is no longer strong enough to keep Earth's axial tilt as stable as it is now. The tilt won't start swinging wildly overnight, but the long-term behavior of the planet changes. Seasonal patterns become less predictable on geological timescales. The stabilizing effect the moon has provided since the early Earth weakens until it's only one factor among many, rather than the dominant one. Long before that point, tides will have already shifted. With the moon farther away, the range between high tide and low tide decreases, and the oceans respond more to the sun than to the moon. The change is gradual, but by the time the moon is tens of thousands of kilometers farther out, Earth's tidal environment will be fundamentally different from the one that shaped coastlines and marine ecosystems for all these years. This threshold, the point where the moon is still visible, still orbiting Earth, but no longer able to regulate the planet the way it does today, is what scientists mean when they say the moon will eventually grow too far away. It doesn't break orbit, but simply crosses the distance where its stabilizing role fades into the background. And that future isn't measured in decades or centuries, but in spans of time so vast that even continents will have rearranged themselves by then. Yet the mechanism driving it is already underway, continuing right now at the same quiet 3.8 centimeters per year that we can measure with a beam of light. The moon's drift isn't something we'll feel in a lifetime, or even in 1,000 of them. But it's a reminder that Earth is a part of a system that's still evolving in ways we can now measure with incredible precision. For now, the moon holds its place, but the motion is real, the trend is steady, and the story of the Earth-Moon system is still unfolding, 1 centimeter at a time.